And welcome to this short demonstration of Rhapsody and SysML and the Harmony process for systems engineering. Now, beginning here inside Doors, we'll open up this initial requirements module here, just to give you some background on what it is you're about to see. This was a document published, issued to us by INCOSE at the INCOSE Symposium, recently held over in Utrecht. And part of that symposium is a vendor challenge. So INCOSE issue a bunch of requirements, and then the various tool vendors that are attending get a chance to show off their engineering knowledge and their creativity, and how the tool sets would actually be used to solve that problem. So this was the document that was issued by INCOSE, and we can bring that into Doors and start filtering it and see that we've got a bunch of requirements here, not too many. The challenge here was to provide a parking system for a chain of hotels. Now we can see here inside Doors there's the original requirement set that we've got, and we started analysing those requirements. Now, some of that analysis was things like Q&A. These were questions and answers asked by various tool vendors and obviously answered by INCOSE. Those are all here inside Doors, so we can actually track them. But then we took that requirement and we actually started analysing it. We started breaking it down here inside Doors. So we broke that original document down, and we've investigated some stakeholder requirements. And again, we can break that down further and go down to system level requirements. And here we've got one: the system shall admit unexpected vehicles when there are unutilized spaces. So the point being, we take these initial requirements down to a certain level inside Doors, and it's the level we're most comfortable, we'll take them forward into the modelling environment. And that's what I've done, and I can select this requirement here in Doors and say I'd like to actually see that inside Rhapsody. And when we do that, in the background there, you'll see that it's automatically navigated down into the Rhapsody tool, and there's the requirement that we extracted from Doors. Now, the different views we can get of that inside Rhapsody. For example, there is the SysML requirement diagram view. Now, there is a diagram that was automatically created actually from the requirements that we brought in. So we can see there are car park access requirements and booking system requirements, and we've got those requirements on a diagram. Now, SysML also has a tabular view called the table view, and we can open that up again inside Rhapsody and see again the same set of requirements and the actual data that we brought in. That's just another view of the same thing. And of course, the real power here is to bring those requirements into the SysML model and actually start hooking them up. And I've got a few examples of that. This is the first one. This is the use case diagram, the initial diagram really that most people see when they're doing SysML models. So here we can see we've got a requirement, and we've brought that in again from Doors, and we've started putting trace links from model elements now to those requirements. So what does that give us? Well, let's flip over here to the gateway tool. And this is what gives us the translation between Doors and Rhapsody. It can bring requirements in, and it can also take the model and push it back into Doors. But it also gives us traceability and coverage and impact analysis. For example, we're looking at the coverage analysis view right now. If I select a requirement on the right hand side, we can see all the model elements that it's actually connected to. In this case, this control entry use case. And again, we'll look at this one, and that's connected to a particular area inside my model. That means if I can see straight away if something changes, if a requirement changes, I can track it straight down to the model elements that are going to be impacted by that change. Now, not only that, we've actually brought in all those requirements so we can get coverage information on them. I can tell right now that 42% of the requirements in my Doors module have actually been connected to some model artifact. Now, when I analysed the requirements, I also brought in some details. I chose a particular attribute in Doors, I chose a status attribute, and I brought that in as well. And that means I can use that as a filter. So for example, right now we have 42% coverage, but if I apply a filter that says only show me those requirements that are agreed, well, that metric will suddenly change. 57% of the agreed requirements have actually been covered. So that's going from Doors to Rhapsody and getting coverage and traceability. So let's go back to the modelling world. Now, this model has been built using the Harmony for systems engineering process. beginning with use case analysis. So here we've decided we have these 4 use cases: controlling entry, control exit, and configuring it and producing reports. We've also decided at this point that the access point here, the physical barrier between the guests or the visitors and our car park, is actually outside our scope. And that gives us some chance to introduce local variations. So if a particular hotel has a barrier or another hotel has a set of spikes in the ground, well, we can accommodate that. Now we begin by taking a use case and performing functional analysis upon it. We do that with a number of views. To begin with, we have the context view, and to do that we use an internal block diagram. And this shows you the system in its environment. So here we've got a block representing our piece of the system, and there are actors around the outside. Now they're communicating via ports, but of course right now we don't exactly know what's supposed to go into those ports. We need further analysis to do that. So we begin with a functional flow. We use an activity diagram to do that. SysML activity diagram that represents all the functional flows through our use case. And we can walk through 1 or 2 of these. So here, someone arrives at our hotel. We don't yet know if they're a guest or a visitor. So we're going to immediately decide that. Are you a guest? Are you a paying guest? Have you pre-allocated a space? Or are you a visitor hoping to just park on the fly? Well, down this path here, we're assuming they are a guest, and then we're going to actually check if they're actually at the right parking lot. One of our requirements was that the hotel could have multiple car parks, and guests could be assigned to individual lots. Well, let's assume that they are in fact at the right lot. That means we're going to go down this route. Then we're going to report the fact that it's a guest, and that might involve talking to the hotel. It might involve flashing up some welcome message so the guest gets a nice warm feeling. And then we're going to open up the entrance. And then we're going to detect the fact that they've actually come in. That's important for us because if they decide not to come in and just drive away, we need to be able to handle that condition too. So on the one hand, we actually don't detect them coming in, so we have this timeout, and we'll just close the entrance. On the other hand, we do in fact detect them coming in. So we'll log the fact that they've entered, we'll update the number of free spaces we have, and then close the entrance. Now over here, let's go back up here. And we have this confirmation of correct lot. Let's assume we are a guest, but we're at the wrong lot. Well, in that case, we're going to check if we can reallocate that guest to this lot, and again, give them a nice warm feeling. If we can do that, well, we'll do so. We'll reallocate the spaces and then report the fact that we've done it and report they're a guest. If, however, we can't do that, well, we're going to have to tell them they're at the wrong place, and we also have a requirement to help them to get to the correct place. Now, having done the big picture like this, we can actually generate sequence diagrams from this, showing the individual paths through this functional flow. So each one of these actions here becomes a system function. Let's have a look at the guest entry scenarios. So this is a set of scenarios actually using a single sequence diagram, showing all the different guest paths through that activity diagram. But the focus here is on the interaction with the outside world, more than the internal functionality. The activity diagram, very, very useful for showing the internal flow of functionality. The sequence diagram, much better at showing the interaction. So here we start with a request for entry by our guest to the hotel, and then we're going to confirm he's a guest and confirm he's the right place, and then if he's at the right place we're going to report he's a guest, and then we're going to open up the entrance. But this isn't described on this diagram. This is an interaction occurrence. We can dive into that and see exactly what that means. Well, it means we're going to start communicating now with this access point. We're going to request that it opens, and we're going to wait until it tells us the fact that it's opened. And then we're going to detect entry. And here again we have 2 possible paths. They don't drive in, so we just time out. Or we actually get this entry detected message from the access point telling us that they have in fact driven in. So we're putting the onus here on telling us that the fact they've entered to the access point. Now, we can do that for all the various scenarios through our activity diagram. The next stage is to design the overall state-based, mode-based behavior for the system. And that we do using, obviously, state machines. There again is our system and its environment, and if we dive into that, we can see the state machine that we described for that part of the system. Now, how do we make sure that all this stuff hangs together? We've got all these different views now of our system at this black box level. How do we make sure it all hangs together? Well, the very best way to do that is to actually execute it. And I've got various simulations set up here. So this one is the black box simulation. We're going to take this model that we've built at the black box level and actually execute it. So there it is, it's actually running now, and we can control it. I'm going to set that model executing, and right now I can see there is no communication between my system and the outside world. And if I dive into this system there, we can actually see what state it's currently in. We're in the entrance closed state, and we're waiting for something to happen. Now I can drive it directly in here, I can start poking events straight into the system, but that isn't really going to test the interfaces between the system and the outside world. So far better is to have my actors actually drive the system. Now in order to do that, I'm actually going to use a web page. I'm going to drive the web page is going to drive my actors. And that allows me to test not only the system functionality, but also the interfaces between my system and of course the outside world. So here I've got a button I can press that will make my guest actor actually send that request for entry. So when we do that, in the background you can see what the system is actually doing. The last states we were in, and the last transitions, the last paths we actually took. So we took this particular path, we sent a message out to the access point to say we'd like to open, and we're now waiting for that access point to open. If we look at the sequence diagram, well, we can see much the same information. The request for entry came in from the guest, followed by these system functions, followed by a request to the access point to open. Well, let's pretend to be the access point now, and again we can push a button here and actually open. So right now the access point message comes in, we're detecting entry, which means of course we have two possible paths. Either we're going to time out here for the entry time, or we'll actually get an entry detected. And since we didn't get an entry detected, this timer here expired, which actually took this route, and of course is going to send this request to close to the access point. Well, that's scenario number one in our behavioral model there, tested. Let's have a look at the other scenarios. And again, I'm going to start pushing buttons to do that, but at the same time it might be quite useful to have another panel. This just shows me just a quick guide really about what this guest might actually be seeing at this point. Now the bottom panel here was auto-generated by Rhapsody, but it's just HTML page at that point. It's very, very easy to go and add your own graphics and bitmaps and Flash and JavaScript, whatever you really want to put in there. Let's start making it look like an actual UI. Okay, scenario number two then. Let's actually turn up with a guest. We turn up, and again the same thing happens in the background as previously, but now we get this welcome message. I can see what the guest is going to see. That's great. Well, this time I'm actually going to open the access point. This time I'm actually going to drive through. And again in the background you can see the entry detected. We've logged the entry and we've gone through our scenario. Alright, well, what happens if I'm a guest and I turn up but I'm actually at the wrong lot? Well, let's see what happens in that event. I turn up, in the background we check the allocations and we can reallocate them. So we do, and I have no idea as a guest that you've actually done that. I get a very nice warm feeling. I can actually drive into the hotel now, completely oblivious to the fact that I've gone to the wrong lot. So that's the idea. At this black box level we can walk through all our scenarios, we can execute the model and really prove at this level that we've understood the requirements, we've understood what the system should do before we go down into actually designing it. Alright, with that in mind, let's actually go and design it. Let's close all our black box level diagrams here. And we'll go down into the actual architecture. So I'm going to start here with this system in its environment, and I'm going to dive into it. I'm going to see what I've used to describe the system architecture. So here we've got a block definition diagram. And I've decided there's my parking system, and it's made up of a detection subsystem and an allocation subsystem, and a UI and an access control subsystem. But are those the right subsystems? I might have chosen those arbitrarily, I might have a good idea, but I really need to actually perform analysis to make sure that that's the right set of subsystems. Well, we've decomposed our architectural view from black box to white box, and we did the same thing for the other views too. For example, I can go in here and see that we've got an activity diagram at this level also. This is our original black box activity diagram, decomposed down to white box level. Now all we've done is literally take the original diagram and slice it up using swim lanes. And each swim lane represents one of our subsystems. And then we drag and drop. We just literally drag and drop into those swim lanes to perform the actual allocation. And again, there are different views of that. SysML has an allocation table. We could see this in a tabular view as well. So we've decomposed the activity from black to white box. We do the same thing, of course, with the scenarios. Now, before we actually take a look at those, let's just have another look at this parking system decomposition. This is shown using a black box BDD, and here we have an IBD. Now it's the same information. We've got the parking system decomposed into UI and detection and allocation access control. But here we can actually see other connections. We can see where our actors are talking to these interaction points, these ports on the boundary of our system, and where messages now are going to be routed down into the internal structure. Well, let's see what messages are actually going to be routed to the internal structure. We've performed the actual allocation of functionality, but we also have the interaction with the outside world to deal with. So, in the same way that we decompose from black to white box with all the other views, we do the same thing for the scenarios. This is the original black box version, and of course this lifeline here now becomes a reference. We can open that lifeline out and see what that means internally. Where are messages coming in and where are subsystems actually communicating? And of course all these provide the basis for population of interfaces and generation of ICDs. And how do we make sure all this is correct? Well, in very much the same way. We can assign now state-based behavior to each one of our subsystems. So we might take, let's say, allocation, dive into that, and again we do state-based behavior for that subsystem. And again, to prove it's all right, we execute it. But this time we're at the subsystem level. So we'll set that executing, we'll click go, and again we can see right now there's no communication. I'm going to start driving that. This time I'll just use the simple panel. I'll just go to the local host and we'll use the free version. So there, again, I have a bunch of buttons. I can pretend to be a guest and it's me, I'm Andy, I'm always in the right place at the right time. So we can see here what happened. All the subsystem level communication. And again, I'll pretend to be the access point and I'll actually open the access point and drive through, and again we can see all the communication that's happening. At that point I'm going to switch my access point there into automatic mode. That means I don't have to drive it anymore, it's just going to open up and let me through when it gets a request to do so. So this time I'm going to change something. I'm going to change a piece of data in the model. So this time it's not Andy turning up, it's Colin. Colin's never in the right place at the right time. So what happens here? Well, we get a request for entry, and here again we can see that communication. And this time we're actually seeing any data that's being passed now between subsystems as we perform this simulation. Well, at that point we've actually got enough information here to give these subsystems to a team and say, you can go build me that. We've got the subsystem definition in terms of its behavior, in terms of its interaction with any other subsystems, and we also have its interfaces. Now those are of course encapsulated into ports here on the boundary. We're not showing the details, but we might choose to create interface diagrams like this one that shows you that allocation subsystem, and this time we're showing the details now of the interfaces in those ports and even the details of the interfaces themselves. Okay, just one or two more things to show you here. Other views we might generate from the information we've already put in. Here we've got this IBD. Well, I'm going to find that here in my browser. There's my subsystem decomposition diagram. Now from those kinds of diagrams we can automatically generate things like n-squared matrices. That's again a different view really of that same information. So there's an n-squared view of my interfaces between my subsystems. Alright, lastly, there was a capacity there to do some local variations. Now, in order to accommodate that, we used a trade study, just as an example of a way of using SysML views to perform trade studies. Let's take a look at that. So here are our original functional requirements. We have some local variations to support. And we took this detection subsystem, and we decided that that was going to be made up of two parts, a recognition part and a redirection part, recognizing you and getting you to the right place if you're in the wrong place. Now for each one of those, we said there were different ways of doing it. For the recognition part, for example, we could have a image recognition camera, we could have a man with a list, or we could have a keypad where we issue a number to a guest before they turn up and then they just punch that in when they arrive. What we also did for each of these was a weighted method study. So here is our recognition part, and here are the MOEs, the measures of effectiveness, the criteria we're interested in: accuracy, speed, fixed cost, running cost. Each one of those is over here as a tag. And each one has been assigned a weight. How important is it in relation to the others? Then for each version, we've got our keypad and our camera and our human. Well, those MOEs have been given actual numbers, real figures. Where did those figures come from? Well, it might be a finger in the air, it might be based on some experience, or we might do a parametric study to support those numbers. Now, given that we only really had 2 days to build this model for the INCOSE seminar, we didn't do a parametric study, but this is a good area where SysML parametric studies might be used. So we did that for the recognition part. We did the same thing for the redirection part. So again, we've got MOEs and weights and actual values for them. What that allows us to do is to decide on some potential solutions. So here, for example, we chose 3. There are more, we just chose 3. We said there could be the very minimalist solution, the bloke with the list solution, and that's using the human and the direction. So for the recognition part, we've got the human, and for the redirection part, getting you to the right place, we've got the man telling you where to go. The high-tech solution was recognition camera and issuing a nice TomTom device pre-programmed to get you to the right parking lot if you're at the wrong one. And lastly, the kind of middle ground, the medium tech solution, was a keypad and a printed map. So we've got these 3 solutions: bloke with a list, high-tech and medium tech, which are these 3. I put them on an individual diagram like this because that allows me again to go into my browser and say I would like to generate a trade study analysis automatically from those 3 potential solutions. And there it is as a spreadsheet with equations, formula actually automatically inserted. So we could, if we wanted to, start manipulating the weights here and see what happened. But here were the results. The last place was the medium tech solution, and slightly better than that, high tech, but right out there in first place was the man with the list, resulting in our final conclusion to INCOSE, which was that you don't need an engineering solution, you just need some cheap labour. Well, that brings us to the end of this short demonstration. You'll find the published solutions of both the Doors side of things and the Rhapsody side of things on the INCOSE website. If you want more information about Rhapsody and about Harmony for systems engineering, please check our website. Thank you for your attention.